Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name is Sean Perry. These are guided notes number 20 in the series on section 4.2, Arithmetic Sequences. Having discussed in the last video what we mean by a sequence, let's now talk about arithmetic sequences. We mentioned them briefly in the last video, but essentially what they are is a special kind of sequence. And there are a couple different ways that we could describe this sequence. The first way is in thinking about them as a linear function, a simple line, except instead of a domain of the whole real number line, we're just going to talk about the natural numbers or a subset of the natural numbers. In my definitions, the natural numbers include 0 and all of the rest of the positive integers, but we could just consider only the positive integers as well, and that's going to allow us to start with the first element of 1. Here is the definition we gave in the last video for an arithmetic sequence. And notice that if we instead call our variable x and our output y, we could rearrange things to get it in y equals mx plus b form. And so this lets us know that number 1 is true. The second says that a sequence is arithmetic if and only if the difference between any two consecutive terms is the same as the difference between any other two consecutive terms. In other words, the difference between two consecutive terms is constant. And although we're not going to cover induction in this course, which is a type of proof, it might be added in later versions of this course. So I will just mention right now how you could go from one form to the other. Let's say the difference between any two consecutive terms was constant. In that case, we could rearrange things as such. Now, notice that at least for the first and second term, this clearly follows from the definition that we gave before. Now, if that were true for some given n, could we get to the n plus 1th term from that? And the idea is, yes, if I rearrange things now with n plus 1 and n, adding my d to n to get n plus 1, if we just replace an with the definition that we had before for an, we could rearrange things to get a sub 1 plus nd. And that is n plus 1 minus 1. So this fits the form, and we've shown that this holds true for every single n. If you didn't follow all of that, don't worry about it. All we're saying is that there are two ways of defining an arithmetic sequence. Either that the difference between any two terms is constant, which means that to get to the next term, you just have to add that constant. Or the definition that came before, where if we want the nth term, we just take the first term and add n minus 1 times d to get this next one, essentially taking n minus 1 steps up from a1 in order to get to an with a step size of d. Now, if we know that a sequence is arithmetic, all we have to do to find its common difference is take any two consecutive terms and subtract one from the other, the latter minus the former. And what we find in this case is that 9 is the difference between any two consecutive terms in this sequence. 14 minus 5, 32 minus 23, etc. Here we have an arithmetic sequence written in standard form, and they want us to compute the first few terms. This is just a matter of substituting values in for n and evaluating that expression. The common difference is the thing we're multiplying by, playing the role of slope here. And the first term is what we would get if we plugged in n is equal to 1 here, which is going to be our 5. For the next one, we're told that this sequence is arithmetic, and they want it in standard form, which is this an equals a1 plus n minus 1 times d form. We note that it starts at negative 16, and that we're going up by 8 each time. So we have n minus 1 times 8 here, and that's all the matching we have to do. Here's another one asking for standard form. We find the first term of minus 14, and we notice the difference between each two of these is minus 2. We go down by 2 each time. So we want to put a minus 2 here. It's customary to rearrange things a little bit and change this plus to a minus if this d is negative. And we could even put the d up front here. It really doesn't matter as long as we have n minus 1 times d, and we are adding that to our a1 term. Now, an advantage of getting things into this standard form is that if we want to know the 15th term, we just have to change n to 15. Here, we're given that a1 is 0, and that we're going down by 6 each time, so d is minus 6. Plugging in 15 into this expression, we evaluate to minus 84. Here's one where we're being asked to solve for n. They ask which term of the arithmetic series is 161. Well, if we are given 161 as our a sub nth term, what's n? This is just a matter of plugging in a1 and our common difference d and solving for n. We can see that the common difference here is 8 by taking the difference between any two terms. And a1 is going to be 1. It starts at 1. So we put those numbers in, and then we solve that for n. This is just a matter of minusing our 1 over, dividing by 8, and then adding 1 to get 21 is equal to our n. So that means 161 is the 21st term of this sequence. Here's another one where we have to find the first term and common difference given two arbitrary elements of the sequence. So we know it's arithmetic, so we know it has the form as given before, and we also know the 5th term and the 15th term. They tell us that the 5th term is 8 and the 15th term is 48. So we could write those down like this, and now what we want to do is figure out what a1 and d have to be. But this is in fact a system of equations. Let's write the second equation up top here. 15 minus 1 is indeed 14. And on the bottom, 8 is equal to a1 plus 5 minus 1, which is 4, times d. Now what we're going to do is subtract the entire second equation from the first one, and this will cancel our a sub 1 terms. This is the same as adding the second equation times minus 1 in row operations. And if we do that, what we're going to find is we have 48 minus 8, which is 40, 14 minus 4, which is 10, and that times d is equal to 40, so dividing by 10, we get that d is equal to 4. If we just take that back to any one of the equations and substitute, we can solve for a sub 1 and find out it's minus 8. So this tells us that the first term is minus 8 and the common difference is 4. So using any 2 points on this sequence, we could figure out the standard form. Very similar to how if you're given 2 points on a line, you can figure out the slope-intercept form. For the next two, we're asked to talk about sums. And there are two different ways we could approach that. We could write down things with summation notation, but we actually have a really cool formula for arithmetic sums. So we're going to be taking the first n terms and adding them up. Let's see how we acquire this equation. It's actually a pretty quick proof. If we know that a sequence is arithmetic and so has this form, we can show that the sum of the first n terms is equal to n times the average of the first and last term. How do we do that? Well, it really is just a matter of writing things down. If I write down the sum of the first n terms, it looks like this. N terms, a1, a2, all the way up to an, added up. Now, if we replace that with their expressions in standard form, we get a1 plus d plus a1 plus 2d, and so on all the way up to a1 plus n minus 1d. Now, if we rearrange things, there are exactly n a1s here, so we could pull that out. There is no d here, but here we have a d, and then 2 d's, and so on up to n minus 1 d's. So if I factor out a d from each term, I could write that as the sum of an index, 1, 2, 3, and so on, all the way up to n minus 1. But we learned in our last video an expression for the sum of the first n minus 1 integers. It would be n minus 1 times n minus 1 plus 1, which is n, divided by 2. Now, that puts an n in this term, so we could factor out an n from both terms. And now, if I want to add these two expressions together, I could get like bases under my a1 by multiplying it top and bottom by 2 and combining it over a common denominator of 2. Let's split up this 2a1 into a1 plus a1, because that's going to let us see that the second term, a1 plus n minus 1d, is just an. And that concludes the proof. So if they tell us the a1 and d parameters here, we're going to be able to find any an we choose for this arithmetic sequence. To get the 12th term, for example, we just substitute n is equal to 12 to find that that's 93. Now we can find the sum using our formula. We do 5 plus 93 divided by 2, and we could take that 2 into this 12 here to get 6. 6 times 98 is indeed 588. For this next one, they even were so kind as to give us the a sub n. They give us a22 is negative 58, and that's the 22nd term, and they want to know what the sum of these terms is. So we just plug in a1, a22, and n itself. And this gives us an expression we can evaluate. 2 goes into 22 11 times, and the sum of these two things is 10. 10 times 11 is 110, and we're done. For this next one, there's actually a few different ways we can go about it. Number one is we could proceed straight away with the formulas from last section. I could factor out a 6, and then say that the sum from 61 to 130 is the same as the sum from 1 to 130 minus the sum from 1 to 60. Now, the sum of the first n integers is given as follows. And if we just take that difference, we get 40,110. But on the other hand, there's another way to look at this problem, which is to see that if we have a constant times n here, we're really talking about an arithmetic sequence. We have a first term of 6 times 61, and each time we go up by 1, we're going up by 6 units. We even know our last term here of 6 times 130, that's 780. So we actually have a1, d, and a sub n. The only thing we're missing for this is n itself. So what is n? Well, we saw how to solve for that in a previous problem. We plug in what we know, and we solve this expression for n to get 70. Once we have a1, an, and n itself, we can plug them into our expression and solve to find the same answer. Here we have a similar problem. We note this sequence is arithmetic, with a first term of 2 and a difference of 4, and our last term is going to be 150. We plug those expressions into the standard form of the arithmetic sequence and solve for n to find n is 38. Plugging these parameters n, a1, and an into our summation expression, we get 2,888. Here we have a sort of word problem. It says determine the seating capacity of an auditorium with 40 rows of seats. If there are 25 seats in the first row, 27 in the second, 29 in the third, and so on. So the idea is we have an arithmetic sequence going up by 2 each time and starting at 25. Now, what is the 40th term of the sequence? Well, we can find that out with our standard form. Plugging in 25, 2, and 40, we wind up with 103. And this tells us that the sum of the first 40 rows is going to be 40 times the average of 25 and 103. This gives us 2,560. All right, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies, and I'll see you in the next one.